Leibniz notation and the chain rule. Let's recall the definition of the derivative. We write the slope of the secant line through x f of x and x plus h f of x plus h as f of x plus h minus f of x divided by h, and take the limit as h goes to 0. This is f prime of x. Leibniz d by dx notation. Let's first define a dependent variable y equal to f of the independent variable x, and we make a picture similar to the one above. Here we use symbols delta x and delta y to represent small changes in the variables x and y. Now, notice that the slope of the secant line is simply delta y divided by delta x. So the slope of the tangent line is now the limit as delta x goes to 0 of delta y over delta x. And our symbol for that limit is dy over dx, or simply dy dx. Notice that in the limit as delta x goes to 0, the symbol delta is replaced by the corresponding Latin letter d. So dy dx is just a symbol for f prime of x, where y is equal to f of x. A particular value of the derivative at x equal to some a is f prime of a, and in our new notation, since there's no slot in which to substitute a, we use the notation shown here, which we read as dy dx evaluated at x equals a. The d by dx operator. The juxtaposition of d by dx with f of x represents f prime of x. So we think of d by dx as representing the operation of taking the derivative. So d by dx of expression equals the derivative of that expression with respect to x. Now instead of d by dx, we will usually read this as the derivative with respect to x. For instance, the power rule can be written this way: the derivative with respect to x of x to the n equals n times x to the n minus 1. Also, for example, the derivative with respect to x of the square root of x equals 1 over 2 times the square root of x. The derivative with respect to x of sine x is cosine x. And the derivative with respect to x of cosine x is minus sine x. So we're seeing that this d by dx operator gives us a convenient way of writing statements about derivatives. The product rule, for instance, can be written this way. We could also write the product rule this way: the derivative with respect to x of u times v is du dx times v plus u times dv dx. And the quotient rule: the derivative with respect to x of u over v equals du dx times v minus u times dv dx all over v squared. The chain rule. This is about differentiation of the composition of two functions f and u. The derivative with respect to x of the composition f of u of x equals f prime of u of x times u prime of x. Written in purely functional notation, the derivative of f composed with u equals f prime composed with u times u prime. Now, in viewing a composition such as f of u of x, we will think of f as the outside function and u as the inside function. Examples: the derivative with respect to x of x squared plus x quantity cubed. Here, our inside function should be thought of as x squared plus x, and the outside function, f of u equals u cubed. The derivative of the outside function is f prime of u equals 3u squared, so we write 3 times u of x squared, and u of x is x squared plus x, and then multiply by the derivative of the inside function. Let's look at the derivative with respect to x of the square root of x squared plus 1. Here we think of x squared plus 1 as the inside function. The outside function is f of u equals square root of u. The derivative of the outside function we know is 1 over 2 times the square root of u. So we write 1 over 2 times the square root of the inside function and multiply by the derivative of the inside function. Simplification here gives us x over the square root of x squared plus 1. More examples. Let's take the derivative with respect to x of sine of 2 pi x. Now here, our inside function is simple. It's simply the constant 2 pi times x. The outside function is f of u equals sine u, whose derivative is cosine u. So we write cosine of u of x, or cosine of 2 pi x, and then multiply by the derivative of the inside function, which is the constant 2 pi. So we have 2 pi times cosine of 2 pi x. Let's take the derivative of cosine squared x. Let's be sure we understand that what this means is the square of cosine x. So our inside function is cosine x, and our outside function is f of u equals u squared, whose derivative is 2u. So we write 2 times the inside function cosine x and multiply by the derivative of the inside function minus sine x. So we have minus 2 cosine x times sine x. The derivative of 1 over 1 plus sine x quantity squared. Here we view 1 plus sine x as our inside function, and the outside function is 1 over u squared, or u to the minus 2 power, whose derivative is minus 2 u to the minus 3 power, or minus 2 over u cubed. And so now we write minus 2 over the inside function cubed and multiply by the derivative of the inside function. So here we have minus 2 cosine x over 1 plus sine x cubed. The composition of three functions. The chain rule here says that the derivative with respect to x of f of u of v of x is first f prime of u of v of x times the derivative with respect to x of u of v of x. Now applying the chain rule again, the derivative with respect to x of u of v of x is u prime of v of x times v prime of x. So we've basically just applied the chain rule twice here. Example, the derivative with respect to x of sine squared 3x. Now the innermost function here is 3x. So let's let v of x equal 3x. Now 3x is inside of the sine function, so let's let u of v equal sine v, and the outermost function is f of u equals u squared. Now the derivative of u squared is 2u, so we write 2 times sine of 3x and multiply by the derivative of sine of 3x. The derivative of sine v is cosine v, and so we write cosine of 3x and then multiply by the derivative of 3x. And since the derivative of 3x is 3, we end up with 6 times sine of 3x times cosine 3x. Now, once one is familiar with the chain rule, you rarely go through so much detail. Let's look at how we would actually do this on paper once we understand the chain rule. The derivative with respect to x of sine squared 3x. The outermost function is the square function, so we write 2 times sine of 3x to the first power, and then multiply by the derivative of sine 3x, which is, again using the chain rule, cosine 3x, times the derivative of 3x. Example, the derivative with respect to x of 1 over 1 plus the square root of x squared plus 1. Now the innermost function here is x squared plus 1, so let's call that v of x. This function x squared plus 1 is inside the function u of v equals 1 plus the square root of v, and 1 plus the square root of x squared plus 1 is inside of the function f of u equals 1 over u, or u to the minus 1 power. The derivative of the outermost function here is minus 1 over u squared, so we write minus 1 over u of v squared, or 1 plus the square root of x squared plus 1 squared, and multiply by the derivative of 1 plus the square root of x squared plus 1. So now we're looking at the derivative with respect to x of u of v. The derivative of u with respect to v is 1 over 2 times the square root of v. So we have 1 over 2 times the square root of x squared plus 1, and we multiply by the derivative with respect to x of x squared plus 1. That's v prime of x, which is 2x. And so finally we have this product. We can cancel 2's here and write the derivative as you see it here. Now again, let's just look at this in its simplest form. To take the derivative with respect to x of 1 over 1 plus the square root of x squared plus 1, we first identify the outermost function here as being the reciprocal function, or u to the minus 1 power. Differentiate that function, writing minus 1 times u to the minus 2 power. Identify the inside function, 1 plus the square root of x squared plus 1. Multiply by its derivative, which is 0 plus 1 over 2 times the square root of x squared plus 1, and then identify the inside function x squared plus 1 and multiply by its derivative, 2x. Cancel the 2's and write the derivative in its final form. The chain rule in Leibniz notation. For the composition of two functions, recall that our previous form for the chain rule is the derivative with respect to x of f of u of x equals f prime of u of x times u prime of x. Now let's omit the x dependence of u and write derivative with respect to x of f of u equals f prime of u times du dx. Now if we define the dependent variable y to be f of u, then we can write the left-hand side of the equation above as dy dx. So dy dx equals f prime of u, which is the same as dy du, times du dx. So the chain rule takes a very interesting form here. Notice that if the two factors on the right-hand side were actually fractions, the du and the dx would cancel out, making it clear that the right-hand side is actually dy dx. But these are not fractions. We don't have any independent meaning at this point of the numerators and denominators of these expressions. But nevertheless, that provides a nice way of checking to be sure that you have written the chain rule down correctly. For the composition of three functions, the derivative of f of u of v of x is f prime of u of v of x times u prime of v of x times v prime of x. Let's think of the function as a sequence of three steps. Given an x, we calculate v, or v of x, and from that value, v, calculate u, and then from u, we then calculate y. The derivative of y, the final dependent variable here, with respect to x, the independent variable, is equal to the product of the derivative of y with respect to u times the derivative of u with respect to v times the derivative of v with respect to x. Again, notice that if these factors were fractions of numbers, cancellation would show that the right-hand side really is the same as the left side. Example. Let's consider the same function in a previous example, f of x equals 1 over 1 plus the square root of x squared plus 1. Now, consider the sequence of steps that's involved in calculating the value of this function. Given an x, we would first calculate x squared plus 1, then substitute that into 1 plus the square root, and then finally calculate y equal to 1 over previous value, 1 plus the square root of x squared plus 1. Now let's give names to the intermediate steps here. From x, we calculate v equals x squared plus 1, from which we calculate u equals 1 plus the square root of v, from which we calculate y equals 1 over u. Now, let's look at the derivatives of each step here. dv dx is 2x. du dv is 1 over 2 times the square root of v. And dy du is minus 1 over u squared. So, chain rule says that dy dx is equal to dy du, which is minus 1 over u squared, times du dv, which is 1 over 2 root v, times dv dx, which is 2x. So we have our derivative there expressed in terms of all three variables x, u, and v. We can now substitute u equals 1 plus the square root of v, as well as v equal to x squared plus 1 into our derivative, and then again substitute v equals x squared plus 1 to obtain the same result that we saw before. More examples. Let's look at the derivative with respect to x of the cube of x squared plus 1 times the square of x cubed plus 1. Now we'll begin with the product rule here. The derivative of the first factor, the cube of x squared plus 1, is going to be 3 times the inside function x squared plus 1 quantity squared times the derivative of the inside, which is 2x. Because we're using the product rule, we multiply by the second factor, x cubed plus 1 squared. Now, we write the first factor, x squared plus 1 cubed, and multiply by the derivative of the second factor. Now, here we use the chain rule. We differentiate the square function and write 2 times the inside function x cubed plus 1 to the first power and multiply by the derivative of the inside function, which is 3x squared. So now let's clean things up a bit. Let's first pull out common factors. 6x is common to both terms, as well as x squared plus 1 to the second power. Another common factor is x cubed plus 1 to the first power, and the remaining factor will be x cubed plus 1 from the first term, plus an x squared plus 1 times x from the second term. Now we simplify that last factor, writing 2x cubed plus x plus 1. So here we have the nice factored form for the derivative. Let's take the derivative with respect to x of x over the square root of x squared plus 1. Now here we begin with the quotient rule. The derivative will be a fraction whose denominator is the square of the square root of x squared plus 1. We begin writing the numerator by taking the derivative with respect to x of x, which is 1, multiplying by the denominator, and then subtracting the numerator x times the derivative of the square root of x squared plus 1. Now here's where we need to use the chain rule. So now let's take the derivative with respect to x of the square root of x squared plus 1. The outside function here is the square root, so we have 1 over 2 times the square root of the inside function x squared plus 1, and we multiply by the derivative of that inside function, which is 2x. Notice we can cancel the 2's in that expression. Now we'll multiply the numerator and denominator of the entire expression by the square root of x squared plus 1. Now, distributing the square root of x squared plus 1 through the numerator, the first term becomes x squared plus 1, and the second term is just minus x squared. Further simplification now gives us 1 over the 3/2 power of x squared plus 1. One more example. Let's find the derivative with respect to x of the square root of 2x divided by x squared plus 3. The outermost function here is the square root function. So we write its derivative, 1 over 2 times the square root, inside of which we have the inside function 2x divided by x squared plus 3, and we need to multiply by the derivative of that inside function. Now the first factor here will simplify by writing it as 1/2 the square root of the reciprocal of that inside function, and now we take the derivative of 2x divided by x squared plus 3 using the quotient rule. That gives us a denominator of x squared plus 3 squared, and in the numerator we have the derivative of the top, which is 2, times the denominator, x squared plus 3, minus the numerator 2x times the derivative of the bottom, which is also 2x. Now we simplify the numerator in the second factor. It becomes 6 minus 2x squared. Now notice that there's a factor of 2 there, which times 1/2 is 1, And also, the square root of x squared plus 3 divided by x squared plus 3 squared will give us a power of x squared plus 3 to the 3/2 in the denominator. So we arrive at 3 minus x squared over the square root of 2x times x squared plus 3 to the 3/2 power.